excited to be here, actually, and I was telling Kip earlier, we've been working very hard to get this paper out. We thought about this for a long time. I'm going to be talking about a paper with the same title, Periodic Table for Black Hole Orbits. And when I say we, I mean, let's see if this is working. This is my graduate student, Gabe. It's a little elongated, actually. We're like 2 graduate students, is the joke. So I've actually identified myself. That's me. I'm the professor. This is my graduate student. We're up till 4 in the morning. This is lovely Columbia student housing. You know how experimentalists always show their equipment? I feel like showing, you know, there's our box of Kleenex when we get very distressed. So we're up all night working very hard on this paper, which we finally produced. I'm really glad to be able to talk to you about it. I just want to tell you, since I know this is a very expert audience in gravitational wave physics, that we're really talking about dynamical systems here. In a subsequent paper, which I hope will be finished by mid-March, by the time of the Pacific Coast Gravity meetings, maybe some of you can see Gabe there talking about it, we'll have a follow-up about its application specifically to gravitational waves. But in this talk, I'm really going to be focusing on the dynamical systems approach, really looking at orbits and how they nest themselves in this system. So to start, and also people should feel free to interrupt and ask questions. To start, what we're really doing naively is looking at spectrums of orbits. We all know that in the Newtonian limit, orbits are simple, regular, elliptical orbits. They're closed. That's what Kepler told us, and we know that that's what happens in the Newtonian limit. We also know that in the relativistic case, even in our planetary orbits, we see things like a relativistic precession. We no longer have closed Keplerian orbits once you introduce relativity. And this will actually be part of what we're talking about. You're excluding something as simple as the closed ellipse, and you're finding that all orbits really have a slight precession unless they're perfectly circular. The story I heard that when Einstein realized that his general theory of relativity could confirm the tiny 43 seconds of arc per century that Mercury precessed in excess of what could be explained, that he had heart palpitations. You know, he called his friends. He said for days he had heart palpitations. He was so excited. So this was the first great test of general relativity. And some of you might remember that some years ago I came here to talk about what happens when you have not one body with a tiny test particle around it, but let's say 2 objects, both of which are rapidly spinning, that you have the possibility for chaotic motion in that scenario. And actually, I'm glad Neil Cornish just happens by coincidence to be here today, because Neil and I worked on this together, where you have chaotic motion of the 2-body system. What I'm going to talk about today is not chaos, so I just want to make that clear. We're going to be looking at this region in between here, before the system becomes chaotic, but yet I'm going to argue that in this strong field regime, there's an entire spectrum of periodic orbits that we haven't paid attention to, that in fact are extremely special in terms of understanding the dynamics around black holes. And the dynamics around black holes is imperative for understanding gravitational wave physics. And I'm going to argue that you can understand the entire dynamics, in fact, by studying this very special set of periodic orbits. So let's start with that. So periodic orbits are special, and to paraphrase Orwell, some orbits are more special than others, more equal than others. It's true that they are a set of measure 0. Very few orbits are actually periodic, but the periodic orbits are very special. So as an example of special orbits, there are things like the circular orbits. We know circular orbits are special. We use them all the time when we think about the dynamics around black holes. What's special about the circular orbits? They're easy to handle, first of all, so the first thing we look at, just naively. And second, lots of interesting orbits, particularly, let's say, low eccentricity orbits, look like small perturbations to circular ones. And in fact, if you're near a circular orbit, it makes sense to look at a circular orbit and to look at a small perturbation around it. So for instance, if I look at a small perturbation to the circular orbit, that's how I derive the precession of the perihelion of Mercury. And that's in fact the usual way people do that calculation, to ask what is the precession of the perihelion of a planetary orbit, is they look at a perturbation to a circular orbit. Everyone with me? Any complaints? Anyone disagree? Any hot tempers out there? So we know that most orbits are not circular. So even though circular orbits are special, they're extremely limited. The punchline here is that most orbits are not near circular orbits. Some might be, but most certainly are not. And so there's no way that circulars can encode the entire dynamics around black holes. And that's been known for a long time. Many very good people are looking at the full spectrum of possible orbits around spinning black holes. What I'm going to argue is that periodic orbits, however, are much more special than circular orbits. Like circular orbits, they are extremely easy to handle. Unlike circular orbits, all orbits, I really want to emphasize this, look like small perturbations to periodic ones. And this is dating back to Poincaré, who suggested that the entire dynamics of any simple Hamiltonian system, and that's what we really have here with the black hole, can be understood by looking at the set of measure zero, the special set of periodic orbits. So I want to emphasize this again. All orbits are near the periodic orbits. And so therefore they can encode the entire black hole dynamics.
So there's some theorem that says this in dynamics?
Well, that's a good question. Poincaré, I don't know how completely general his theorems are. Neil, actually, do you know how general his theorems are? I don't know all the systems that you can prove them for, but I can show in this system that we'll be looking at that you can prove just by simple number theory arguments that the periodics are, in fact, in this case, dense in a phase space. Yes.
If I want non-equatorial orbits,
right.
Is there a theorem that says that?
To be honest, I can't think it's a theorem or a conjecture. Right. So we do know, I mean, as Kip and I discussed earlier. Sorry, what was that? Exactly. So what we're going to do is we're going to show that the periodic orbits in the equatorial case are mappable to rationals. But we also know ahead of time that in the non-equatorial case it's mappable to rationals. And we discussed whether it's two rationals or one. It's open for discussion. But since the rationals are dense, again, you can argue in that case it's clear that even in the non-equatorial case, maybe I should be more forceful, even in the non-equatorial case it is clear that you're going to be able to encode periodics with rationals and that rationals are dense. So
the recurrence theorem strictly says that every orbit, if you wait long enough, is nearly periodic. It's not the same statement, but something like that plus.
You know what? Actually, you can combine those. So good. So it must be an exact theorem. You can combine that with the argument that since we know the Kerr orbits are restricted to n-dimensional tori, and we know that any aperiodic orbit will fill out the torus, and the periodic orbits are going to be individual cycles on those tori, that you can prove that every aperiodic orbit is always epsilon close to some periodic. So you can do it through the Hamilton. Well, that's a good question. If they're stable. If they're unstable, they move off and go near a different one. Okay, so all they can do, imagine a phase space where it's near an unstable periodic orbit. It can move away from that because of the instability, but it will just find itself on a different one. A lot of what we're going to be talking about, these are primarily stable, so that it stays close to them for a long time. But there's a better answer, which is that, I'll show you in the next slide. There's a statement about being near in the perturbative sense, and there's a statement about being near in terms of how precisely you approximate any irrational by a rational, and in that sense it can stay near arbitrarily long. Okay, so I'll show you in a second. Okay, so now basically that was my whole seminar. So for those of you who are really fast, you can go get a coffee. So periodic orbits, the argument again is encode the entire black hole dynamics. And so to show you, this is the preview that I was just promising Mark. What I'm going to show you in this talk is encapsulated in this figure. So everything I'll do for the rest of the talk is going to be justifying a figure like this. On the first row is exactly periodic orbits. And this is a simple one. I'll tell you what they mean and how they fit themselves in phase space. I think somebody really smart left because they felt they got the whole. Did you see that? So here's a simple orbit which has one leaf world. Here's a three-leaf clover. And this one I'll tell you later why it's a three-leaf clover. In the sense of perturbance, which is the one you said you liked, I can think of this as perturbations of this guy. This orbit has the same energy, the same angular momentum, the same angular momentum, the same spin, but a slightly different energy. And as a result, a slightly different also, however, do better and say, actually, this is arbitrarily close to exactly periodic orbit. I generated this on a real computer. The computer truncated the numbers at some point in the decimal expansion, and this is actually an exactly periodic orbit for that reason. I can never generate an aperiodic orbit in reality because it requires an infinite list of digits, and I can never get that far. So in other words, if there's an irrational associated with it, every irrational in reality is approximated by the rational. So I'll explain why I'm mapping this to the rationals in a second, for those of you who didn't read the paper preemptively. So there's two senses, just to repeat again, in which this orbit is near this one, is near a periodic. It's near this one as a perturbation to it, because it's accepted around it. But it's also near a different periodic orbit with some better properties. So we'll talk about those two cases. To begin, even though we're not restricting ourselves to Schwarzschild, I think it's very advantageous to look at the Schwarzschild metric because it allows you this very nice reduction to one-dimensional motion. It's well known that when there's no spin from the central black hole, that I can look at the motion of a test body around this non-spinning black hole as motion in a one-dimensional effective potential. I have a kinetic energy and an effective potential energy, and this equals the energy squared over 2. And the effective potential is built by using the conservation of the angular momentum to eliminate angular degrees of freedom. So this is a very interesting and important picture because, as everybody who studied this remembers, there are two important orbits. This is that early transparency. We know the circular orbits are special. If I'm sitting here at this minimum of this potential, the radius is not changing. I'm at a fixed point of this one-dimensional system. And I have a stable circular orbit. If I perturb it, I get the precessing Mercury-like rotation. There's also an unstable circular orbit, a very well-known unstable circular orbit. And for our case, what's interesting is there's also a homoclinic orbit, a less well-known, but an orbit that has been raised in literature from time to time. This orbit has the same energy and angular momentum as this unstable guy. Imagine I start at this point in the potential, same energy, same angular momentum, but it's a different orbit. As I roll down, I'm coming in from far away, and as I slowly approach this unstable fixed point, it whirls an infinite number of times as it approaches that unstable fixed point. So this homoclinic orbit formally approaches the same fixed point in the future and the past, and it's an important orbit in dynamical systems theory. We actually know how to write down an analytic expression for this homoclinic orbit in the Kerr space-time. Hopefully you'll see that in the archive soon, but not just yet. Now, if we look at this effective potential diagram again, just to recap, what do we usually do? Well, the lowest energy orbit for any given angular momentum is always the stable circular orbit. And the highest energy orbit is the homoclinic guy, at least when the angular momentum is low enough that I have this bound unstable circular orbit. Now, in between, this is a kind of energy level diagram, is my infinite number of periodic orbits. And the argument is that they are absolutely dense in this energy space, that wherever you land, I want to draw a line. I say, oh, here's a real orbit at this line here. I can tell you that there must be a periodic orbit arbitrarily close to that. And it's because of this kind of an energy level diagram that we have the ability to find a periodic table for these black hole orbits. So let me tell you how we're going to do that. So this is really where the story begins in detail. We know well what the orbits are around a spinning black hole. Carter found that there were enough constants of the motion. In the 1970s, he realized this, that if I have a non-spinning test particle around a rotating black hole, that the motion is formally integrable, and he was able to write a nice, concise way of expressing the geodesics, at least in differential form, around a rotating black hole. He realized that there was a conserved energy, a conserved angular momentum, that the rest mass of the particle is conserved. This is the same as saying there's a conserved Hamiltonian, if you like, and that there was a new quantity called the Carter constant related to a time-like Killing field, and that last constant was what allowed him to famously reduce the orbits around the black hole. Now, even though in principle I can write down a simple differential expression for all of these orbits, it doesn't mean I know much about them. It's been going on for years, and people realize they're very complicated and have still been trying to study the behavior. So all we're doing is looking at that dynamical system, and we're finding that, that set of special periodic orbits in that energy level diagram, if you like. Are there any questions before I go into the taxonomy? Oh, it just said, therefore, motion lies on tori and is inevitable. For a Hamiltonian system of n degrees of freedom, if you have n constants of motion, it's simple to show that in an action angle formulation, you can always line up the momenta with each of your constants of motion, so that every coordinate in that action angle variable becomes cyclical, becomes like a ring, and so you have an n-dimensional torus. So for Hamiltonian systems, it's not. Okay, so I mean, I skipped over it because I didn't know if people wanted to hear that level of technicality, but if you like it, I can do that. So the taxonomy of periodic orbits, now what I'm going to try to do here is just give you the essential taxonomy in terms of just topological features, and then I'll try to link it to the rational numbers for you. So just again, we're looking at not chaotic systems. We're looking at the Kerr metric. We've restricted ourselves to equatorial because you do what you can do first, although I'm pretty confident we know how to do the non-equatorial case. And to bound non-plunging orbits. And the first point, actually, in the taxonomy, let me go ahead to this, is here is an example of a periodic orbit. I've only drawn in this first figure one radial cycle. So an orbit which starts at the apastra, at some furthest point. It comes in, it goes 2 pi around, but I can never come back and close after 2 pi, because we know in relativity there are no closed Lewis systems. They don't exist in relativity. So the first thing I can do is I can go all the way around to the next step out. So that's one radial cycle. Here's the full periodic orbit, going all the way around and closing. So here I go 2 pi around, and then I go another pi. So the accumulated angle in one radial cycle is 3 pi. Here, this is just an example of a periodic orbit. And I'm going to, oh, sorry, x and y, physical position around the black hole. So imagine the black hole at the center, and here's my test particle leaving an ink mark as it goes around. So here is an example of a central orbit. I just built a taxonomy. So I'm not ordering them yet in energy. And here is the complete closed cycle. So I call this orbit a 2-leaf orbit, or we label it by an integer z. In this case, z equals 2. It stands for zooms. And we're referencing a zoom whirl nomenclature that exists in the literature for a long time, and we thought we'd retain that moniker. So just for continuity with that previous literature, we'll call these zooms. Now, we're not done. We could say, so here's all our periodic orbits. All I have to do is say how many leaves an orbit has, and I specify the orbit. But that's not sufficient to specify the orbit. So here's another 2-leaf orbit. Here's one radial cycle. And notice in this one, I go 2 pi around, but then I whirl around the center another full 2 pi before coming back out to apastra again. So this is a unique orbit. It went around 5 pi in accumulated angle in one radial cycle, 10 pi for the whole orbit to close. So this orbit is a 2-leaf orbit with one whirl. And this is the zoom whirl nomenclature I was referring to. Right, the zoom is the number of times it gets to the apastra before closing. And the whirl, we're counting only in one radial cycle. So this guy's whirled twice. Okay, but we're going to call it a 2-1. So we're calling it by radial cycle. Now you might think you're done. Now you might think, now I've specified every geometric property I could about a periodic orbit, but actually we haven't. There's some very interesting properties. All the orbits in 3 leaves or more trace out polygons. Very beautiful symmetric properties. Here's a 4-leaf orbit that traces out the vertices of a square. And this 4-leaf orbit whirls once. So here's one radial cycle. It comes in, it whirls around once, and it comes to the next apastra that it could possibly come to. Okay. This one is also a 4-leaf orbit, and it also whirls once. However, it skips 2 leaves. It comes around, It whirls a full time, and it goes to the third leaf in this four-leaf pattern. These are energetically distinct orbits. Okay, they are different orbits. It's a very good question. This angle, this accumulated angle, can be expressed as an integral over geodesic equations. An integral over d phi dr from one apastron to the other, or twice the integral from perihelion to apastron. And we don't have an analytic expression for that integral, but I plan on going back and hammering at it a couple weeks longer. I'm not convinced we can't get an analytic expression, but we got over anxious. We could do it numerically, so we just, we're a little trigger happy. I'm pretty sure we'll be able to find an analytic expression. And as Dr. Minnow and I were discussing earlier, it would be very nice to do so, because then you can know general things about the behavior of the rational numbers. And okay, so but just this is actually key, the accumulated angle. So if you look at counting it again, I always go 2 pi around. With each whirl, I go an extra 2 pi around. And what vertex in this polygon I make it to determines, so this guy goes another pi over 2, but this guy goes a 3 pi over 2 extra. So the vertex number in this ordering, if I count the first apastron 0, and then I label the vertices of the polygons as I go around, the vertex over the number of leaves gives the additional accumulated angle in one radial cycle. And right here, you're going to start to see the rational number, that we've basically derived that rational number. Okay, now I'm deriving the rational number purely, I'll get to it in the next transparency, purely on topological and geometrical grounds. Okay. Good, excellent. I forgot to say that. I'm really glad you asked me that. Let's look at the one that goes to the second. So if I went around here, I whirled once and I went to the second guy. Then I went again, I would close. So actually that guy is not a unique orbit. It's the same as this guy. So only orbits where V and Z are relatively prime are unique orbits. Okay? So in other words, and we'll find that the rational number associated with going from here to here is the same rational numbers for the 2-leaf, 1-whirl orbit, not for the 4-leaf, 1-whirl orbit. Okay? So if I tried to say, oh, it's a 4-leaf, 1-whirl orbit that goes to the second vertex, I would see that the rational number associated with that is really the rational of the other guy. Okay? So the rationals are unique to each orbit, and they have to be relatively prime. Okay. Before I go to the rationals, I want to point out, which is relevant to some of the questions that have come up, that high Z orbits, orbits with lots and lots of leaves, actually look like processions of low-leaf orbits. It's a very nice feature, and it's because of this vertex behavior. So here's an exact 3, 1, 1. It means it has 3 leaves. It whirls once in the radial cycle, and it goes from the first vertex, from the 0th vertex, to the next one in the sequence. Here is an orbit that's very, very, very close to this one energetically. It differs in the 4th decimal point. It has 300 leaves before it closes. It only whirls once in each radial cycle, but it doesn't go to the next leaf in the pattern. This is fundamental. It skips 102 leaves so that it comes all the way over here. And it keeps doing that, skipping 102 leaves until you go 300 times and it finally closes. So the exact periodic orbit that it is, and this is the point I was trying to make in that earlier picture, it's exactly a 301, 103, but it's very close to a procession of this guy. It's a really nice feature. It's a really nice feature. Okay, does everyone appreciate how nice that feature is? It's a very nice feature. I was very excited about that. Okay, so we've derived that there's a relationship to the rational numbers on purely geometric grounds. Here's my accumulated angle, and I can fix it based on these geometric properties, W, V, and Z. It seems like I need 3 integers to label an orbit, but really, I only need one number. This one maximum number here, which is the number of whirls in a radial cycle, plus the vertex I jump to over the number of leaves. And that this rational number uniquely specifies every periodic orbit. So we've geometrically derived that every periodic orbit is mappable to a rational number.
So if you tell me that number, you know the orbit.
Yes. For given L and E, for given L and A, for given spin, I should say, by A I mean spin of the central black hole and a given angular momentum. So 2 different angular momentum might have the same Q, but they're unique orbits. So exactly, we can find all of the periodic orbits, as you preemptively asked, by integrating the Kerr equations subject to the condition that the accumulated angle be fixed by this rational. And that's how we find them. That's how I've drawn those pictures. Okay? And if I could integrate this analytically, which I think we can, then we'll be able to write that down analytically. Really nice. Here's another derivation of Q. Every equatorial orbit has two fundamental frequencies. Here is the radial period. So the fundamental frequency associated with that radial oscillation is always 2 pi over that radial period. The angular frequency average over a full TR, over one radial cycle, is defined as the average of the angular frequency over one of the TR, is the definition of what we were talking about with that accumulated angle. Omega phi, the average, to say it again, of phi dot, essentially, the rate of change of phi, in one radial cycle is what we mean by that accumulated angle over TR. And so the ratio of omega phi to omega r, is that accumulated angle over 2 pi, which we just said is 1 plus our rational number. And if you are comfortable with dynamical systems theory, you might know ahead of time that there are going to be fundamental frequencies, in this case omega r and omega phi, that you can derive from an action angle formulation that Sean and I talked about in the case of looking at Hamiltonian dynamics, and that they are rationally related for periodic orbits. So you know that there's a rational relationship between omega phi and omega r for periodic orbits. And we've just re-derived it totally geometrically. So that what we've been able to do is we've been able to identify how this rational is related to certain topological properties of every orbit. Its zooms and its whirls and its vertices. Okay. I'm going to skip that transparency. People can ask me about it. It's just there in a case of an emergency of how circulars fit into this. Circulars, I'll just say a little bit, are awkward in this classification scheme because they're not periodic in the normal sense because they don't have a radial oscillation. So they're not periodic in the sense that we've been describing. But if I perturb a circular, omega r is its stability. It has to do with the stability of oscillations. And omega phi is its typical phi dot. And in fact, there is a Q associated with stable circular orbits. So I can just, if people want to see why that's the case later, I can talk about it in more detail. So let's revisit our energy level diagram. We know at the bottom we have some Q for the stable circular orbit. At the top, we have some Q of whatever the maximum energy orbit is. And in between, we have the rational number associated with every periodic in here. And so the next exciting fact is that Q is monotonic in energy. And what that means is that it's bounded from below by the Q of the circular orbit, the stable circular orbit, and it increases until it hits the Q of the maximum energy orbit. And by that I mean either it crosses this line, so potentials would pop above that line, it hits the equal line, or it's the Q of the homogeneous. Okay, the maximum energy bound orbit for that L. So this means that if I know the upper and the lower bound, I know everything about the spectrum of periodic orbits permitted. And you get every value in between. And you know, when Neil and I looked at cases where there were chaotic systems, that's not what you find. You find pruning and you find complicated grammars based on things like those topological features. So this is not, this is simpler.
So for the non-periodic orbits,
For the non-periodic orbits, Q would not be rational. There would be an irrational number. Yes, because every real orbit is approximated by a rational number. Between every, so here, this is good. It's good that you asked that. So let's put it this way. Well, I do in the sense that what I mean by Q is irrational. Okay, so every rational is dense. So let's say, so here's a half and here's a third in that energy level diagram. And in between are some irrational numbers. There's also some rational numbers. But there's a well-known theorem. So any real orbit is actually associated with some irrational with an infinite list of digits. But every irrational can be approximated by a rational because the rationals are dense on the number line. That's all I'm saying. I guess I didn't really need to draw this, did I? Yeah, maybe it helped. So, and you can say to what approximation you want to approximate any rational by any irrational by a rational Q. Okay? So it's true I would make that dense with lines, but in between that's still a set of measure 0.
If the Q's are close, it'll look close as a picture.
Right, so look at the Q of the guys that I drew before. Let me go back and actually show those because, sorry, were you going to ask something before? So let's look at this guy that I said, these two, okay? The Q of the first one is 1 plus a third, right? And the Q of the second one is 1 plus 103 over 300, which is pretty close to a third. Nice, huh? Cute. I know. That's why I was sitting there in my graduate student's apartment until 4 in the morning eating takeout. Okay, so let's go forward again. Okay, and it's because of this that that we're able to know what the spectrum of the periodic orbit is. And again, that's what allows us to build a periodic table. So let's start to look at some of these periodic tables. It'll take us just another minute to get to them. Let's consider, just to reassure you we haven't done anything wacky, the weak field regime, and be sure that we don't find something suspicious there. So here's the effective potential for solar system values, simply. And that the potential now looks as though it has a centrifugal barrier that's classic of semi-Newtonian looking potentials. And there's the E equals 1 mark. So by the maximum Q, I now mean the Q of the bound guy, the first bound guy, the E equals 1 guy. So that's my maximum Q. Well, that's okay. My minimum Q is the Q of the stable circular orbit at the bottom. And what you find is that they're both much less than 1. They both approach 0. And that means that there's no whirls. Thanks God. We don't want to start saying that planetary orbits are going to whirl. They don't whirl. And that most of them look like V1 with a very, very large Z. So they look like Mercury-type orbits. They very tightly stack lots and lots of Z's. So as an explicit example, imagine we actually had Mercury, 43 seconds of arc per century. It has an orbit of 88 days. I typed it into a calculator and I got 0.3 seconds per orbit. And that should come to 360 degrees, and we went all the way around, divided by this given number of leaves, 3,600 squared. Okay, so I divide that whole ring into the number of leaves. So Mercury has close to 10 million leaves. It's very close to an exactly periodic orbit with 10 million leaves and no whirls, what we would call a 10 to the 701. Not a very useful classification in the weak field, but at least we're reassured we didn't, prove Kepler wrong or something terrible like that. So in the weak field limit, in fact, orbits are Mercury-type precessing ellipses. But what happens in the strong field? In the strong field, this potential starts to resolve. I see that it's not actually a centrifugal barrier. The angular momentum is dropping. I see that there's an unstable circular orbit on top there. I'm going to actually skip ahead to the case where it drops enough that all of the orbits are below 1. So this point, we call this, I know people call it different things, an IBCO, an innermost bound circular orbit. So let's call this the strong field regime, and that's what happens in this other extreme scenario. So with that innermost bound circular orbit, we've already argued that every one of these guys has associated with it a homoclinic orbit, an orbit with exactly the same energy, exactly the same angular momentum. Imagine starting it out here. It would roll up its potential towards whichever one we're talking about, and whirl an infinite number of times as it did so. So as soon as that IBCO appears, it means that the maximum Q, so now my bound becomes Q is bounded, the rationals are bounded by a stable circular orbit rational number all the way up to infinity. So the next question is, what is QC for the different x? In fact, is QC 0? And it better not be 0, because that would mean there's a closed ellipse. But what is it if it's not 0? In other words, are all Q allowed? Are all periodic orbits allowed? And I think this is one of the most interesting results we have so far. The answer to that is no, it is not. So let's look at how that works. here is the same range of potentials. These are the different angular momenta associated with it. We're still doing spinless. I'll show you spinning pictures in a second. And this plots that rational number q as a function of the energy of the orbit. And this plots that rational number q as a function of the eccentricity. It doesn't really matter which picture you like to look at. I'm going to look at this one just because it most clearly shows that there is a limiting value for q. Q does not go down to 0. This number is the q of the circular orbit. The eccentricity increases as I move away from the circular orbit, and q increases quite slowly for the spinless case, more quickly for the spinning case, and diverges as you approach the homoclinic guy, and it starts to whirl an infinite number of times. This fact means, let's look at these guys. They all asymptote around a half, this little cluster down here. The half, q equals a half, corresponds, if you remember in this breakdown, to 0 whirls and 2 leaves. Okay? So it means that as I move slightly away from circular, the first guys I'm going to see look like precessions of the 2-leaf no-whirl orbit. They do not look like Mercury. So I think that's the first interesting result. Mercury looks like a q nearer 0. And Mercury is stable. The first, I think, really interesting, here's our first periodic table. If I'm stacking in this table q or energy at the top increasing as I go down these columns, this would be q is 0, which would be the Keplerian ellipse is excluded. This is a q, I'm just doing discrete jumps because there's an infinite number of reactions. This is a q of a third, and it's excluded. Angular momentum only. So I look at, in the Schwarzschild case, let's say I look at this angular momentum here, this line here, and it tells me that none of the orbits have a q below that means none of them have a q for third. So the 3-leaf no-whirl orbit gone. It's not there. I will never see a 3-leaf no-whirl orbit with that angular momentum. Okay. And these numbers get more extreme as we go to the Kerr case, meaning you start to see more and more whirls sooner. You start to see more stuff excluded. So this guy's gone. The 3-leaf no-whirl orbit's gone. So here's one that I do have, something that's very close to a half, which is a 2-leaf no-whirl orbit, something that's very close to 2/3, which is a 3-leaf no-whirl orbit that skips to the second leaf. So the 3-leaf that went to the first leaf is there. The 3-leaf that went to the second leaf is there. Now I start to see them with whirls. Here's a 1-leaf. Sorry?
What have you changed?
Nothing other than I ran out of space, so I'm going to go up here and keep going down it. It would be nice to have them like a movie or something. So here's energy just increasing. Okay, so now as energy increases, I have q of 1. I have a 1-leaf 1 whirl. I have a q of 1 1/3. A 3-leaf 1 whirl, q of 1 1/2. A 2-leaf 1 whirl, q of 1 2. And then I have the same thing, but now q has an extra integer because it whirls an additional time in each column. And I can keep doing this where it whirls now 3 times, 4 times, until eventually you go to infinity with the homoclinic orbit. Okay? You start to see the progression. Now it happens that in the Kerr case, the low eccentricity lines that curve is pretty flat, and it only diverges. You start to see nice, interesting patterns, but you don't see lots of whirls until you get pretty close to the homoclinic. Yeah. You can ask. You can ask me. I know Kip's really, really smart, but I'd be asking Kip too. So here's another. Okay. Well, you know what? It's slightly crummy resolution actually on my figures, and they're not labeled by Q yet. I should have a little Q in the corner here, which would be nice. It is the energy. Yes, the energy is increasing.
I didn't want to bother you with that.
That's okay. I love it. I love it. Okay, so here again is a column. Sorry, this is a row from the previous diagram. This is the 1 whirl row from the previous diagram. I haven't plotted every one that was in the previous diagram, but I've plotted the 1-leaf 1 whirl, the 3-leaf 1 whirl, and the other 3-leaf 1 whirl. And down here is the one that I didn't plot previously. It could be included. It's one with 1,000 leaves that jumps to the 9th as they go around. It looks very much like a procession of the one above it. And this one has 1,000 leaves and jumps to the 337th in the pattern before it keeps going around. And it looks very much like a procession of that one, et cetera, et cetera, et cetera, as you go down. And the only thing that I'm really doing is I'm moving again through energy. I move the energy slightly. And it's true I end up with a high leaf orbit, but instead of panicking about that, I realize, oh, that looks a lot like a precession of a low leaf guy. And now I keep going, increasing in energy, and eventually this guy gives way to look like a 4-leaf guy, and eventually that gives way to look like a precession of the 4-leaf guy. The energy increases, and now I keep going through a third, processions of a third, etc. So it shows you how, as you cross, and this is the same as this example, as you go from a third to a number very, very close to a third, you look like a procession of that low leaf guy. So if Z is large and V is large is another way of saying it, you're probably better off looking at this as a procession of a low leaf guy. Okay. And so why that's interesting is when we get to using this for gravitational wave astronomy, we don't want to have to go to huge numbers of leaves to understand the classification. We always want to see the low number of leaves. It means we only have to compute a smaller number of orbits, if you like, and look at the others as processions of those low leaf guys. So let's look at the Kerr case. Here's a Kerr case where it's spinning quite rapidly. Just to be extreme, I went all the way to 0.995. And what I want you to notice, again, I'm plotting that rational number q as a function of energy, and that rational number q as a function of eccentricity. And what I want you to notice is all of these asymptotes above the number 1. And that means that they all whirl at least once. Every orbit for this spin whirls. I didn't know this going into it. I thought whirls, this zoomy whirl behavior, was strictly for nearly homoclinic orbits, orbits that were very close to approaching that unstable guy and were nearly homoclinic. These are not nearly homoclinic. These are low eccentricity, the perturbations of the stable circular orbit, and they all whirl at least once. Okay, so it's already interesting. And so this is saying if I were to do a periodic table for this guy, as you do here, I didn't draw the exclusions. And it's not that necessary to go through in detail, but you see everyone whirls at least once. So all of these are 1-whirl guys, all of these are 2-whirl guys, all of these are 3-whirl guys. And we showed a pretty low eccentricity case, just for fun. And again, in the next picture, showing some that we had suppressed in the previous picture, the 1-leaf, 1-whirl, and its near neighboring energy, and like a procession of it. And the same as before. So again, these are just organized in terms of small changes, very tiny changes in energy. Okay, so let me recap what I think we found. For a given A and L, we know that there's a rational associated with every periodic, that it's bounded from below and above by simple things that you can determine. In the Newtonian limit, those boundaries approach 0, as you hope, so you only have things like precessing ellipses. There's a no-zoom whirl behavior in the weak field regime. That's good. At the ISCO, the innermost stable circular orbit, both the lower and the upper bounds start to approach infinity. The ISCO actually has 0 eccentricity, so it's not that interesting just at the ISCO, because how can you tell a zoom from a whirl if it has 0 eccentricity? But it means that as you approach the ISCO, whirls become more and more and more predominant. In the very strong field regime, you're always bounded above by infinity, because you whirl an infinite number of times at the homoclinic. And in the strong field regime, the simple precessing ellipse from planetary orbits is forbidden. That's very interesting. All aperiodic eccentric orbits can be understood as precessions of low-leaf clovers. And again, as the ISCO, which is kind of redundant with the claim I made earlier, that as the ISCO is approached, all orbits will zoom and whirl for any value of A. It's just a matter of whether or not we can resolve that eccentricity. Okay, so how am I for time? Anybody have any idea? Okay, I'm not going to take the full 12 minutes. I don't think. I want to stop for, hopefully there will be questions. Let me tell you why I think this is useful. One important application of this, besides the fact that it's kind of neat, is that I hope it's going to have profound implications for gravitational wave astronomy. First first of all, extreme mass ratio in spirals are going to be on eccentric inner orbits. That's the latest projections. And if we're arguing that all eccentric orbits show this behavior, it means that we will see this as an observable when we get to the point of launching LISA, which is hopefully not too far away. And it will also hopefully be useful in data analysis techniques. We're looking at a time frequency analysis where you're looking for harmonics of some fundamental frequency as a natural way of searching for these orbits if they look like they're all close to the three-leaf clovers. And you're looking for a pattern in the fundamental harmonics appearing in a time frequency analysis. And I think it could be a really fruitful way of trying a different data analysis technique. Computationally, this is what we're working on now, and again, hopefully, if you get to see Gabe, you will now recognize him from that picture. You can see him at the Pacific Coast Gravity meeting. I'm hoping we'll be done by then. We're going to discuss how, instead of looking at things like the Tucholsky equation for generic orbits, the Tucholsky equation is a way to understand gravitational energy and angular momentum loss and back reaction, that instead you would float in on these periodic orbits. And by doing so, you could have the computational advantage of Fourier decomposing those things in terms of one frequency instead of three. And those who do this know how computationally expensive it is to have three fundamental frequencies. That's for the full non-equatorial case. So what we're hoping to have is a major computational advantage in terms of cost of computing coefficients in things like the gravitational wave back reaction calculations. And another, maybe less important aspect to most, but interesting to me personally, is that you can watch a spin transition to chaos. So I'm just going to really quickly, I'm not going to show most of these slides, I'm just going to make one point. Even though I said we know what happens in the system with the test particle around the curved black hole, it's quite different when the companion spins, because you lose one of those constants of motion. The system is no longer integrable, it's no longer confined to tori, and you have the possibility of chaos. This is also true when you have two rapidly spinning objects of comparable mass. So not a test particle, but two of comparable mass. And the only point I really want to make here is that if we look at this kind of analysis of studying it through dynamical systems, we know that periodic orbits continue to define the phase space. That's true even in a chaotic system. And we also know from famous theorems dating back to Arnold and Kolmogorov and Moser that chaos develops around certain unstable periodic orbits. It sounds like a lot of dynamical systems preemptive stuff, but what you know, therefore, let me just show this latter picture, is what happens around the homoclinic orbit is what's very interesting as you turn on spin and you watch a transition to chaos. Because it's the homoclinic orbit which forms a boundary. If I think about this as being the unstable circular orbit, there's a direction in which if I kick around that black hole, I'll move away from it. If I time reverse, I approach it from the homoclinic side. This is literally the homoclinic orbit in phase space. So this is a phase space schematic of what that fixed point looks like, stable and unstable directions. And all I really want to point out with this slide is that as it transitions to chaos, this becomes a tangle. That simple homoclinic orbit for which we have an analytic solution becomes a tangle of an infinite number of intersections of the stable and the unstable manifolds. And what you've really done is packed an infinite number of periodic orbits in this region, but now they're unstable periodic orbits. And those form a fractal set in the phase space. And so if you did come to the camp a couple of years ago, that's what I was talking a lot about, finding those fractals. And that's stuff that Neil really did a lot to introduce that technique. Sorry, I'm skipping these slides because but they're slow. Okay, so those are some of the fractals which I won't be telling you about. So we already, but the funny thing is that we found the fractals before we found the homoclinic orbit. Because in a way, it was easier to go straight for the fractal in the fully chaotic case and uncover that there existed a fractal. And now we're going back to scratch and building up these periodic orbits, and we'd love to watch that transition happen, to see those cues that order themselves so nicely in these periodic orbits begin to form a fractal set, fractal tree. And you see that a lot when you look at how the rational numbers order themselves and how the irrationals order themselves. Anyway, okay, so enough chaos for now. We don't know whether or not we'll ever observe chaos in the dynamical system because it's damped by gravitational waves, and we still, I don't think, can conclusively say whether it's completely damped or observable. It's in a very gray area. We well know that the post-Newtonian calculations that we use for comparable mass binaries isn't relativistic enough, and the Kerr case, the spin of the particle has to be unrealistically large because you're not including the actual mass or the perturbation to the gravitational field of the particle. So it's sort of in the one region we don't know how to calculate whether or not we can still see chaos. But I think the numerical relativists will resolve this for us, whether or not we'll see episodes of chaotic scattering. So just to conclude briefly, the first test of general relativity was the precession of the perihelion of Mercury. It's almost a century later, and what we're still looking for really is precessions of orbits. And it's just very nice that now we're looking at precessions of multi-leaf orbits and these zoom whirl patterns. And again, optimistically, maybe we might even see something like transitions to really complex behavior, like chaotic behavior in a final mission. Thank you very much.